Okay, let's take a look at Chapter 2 from the Organic Chemistry ACS Study Guide. And Chapter 2 covers nomenclature and functional groups. So we're going to skip right ahead through the practice questions. And we'll start with these questions here. Okay, practice question 1. What is the IUPAC name for this compound? You can see we've got an alkane here. And so what are we going to do? We're going to find the longest carbon chain. And we want to give the first substituent the lowest possible number. But if you look here, we have 1, 2, and we have 2 methyl groups here. And then if we were to start numbering over here, we have 1, 2, and we have a methyl group here. So in terms of which side is going to be the highest priority, it's going to be the one on the left. And the reason why is because here I have 2 methyl groups. So if I put all the numbers on the longest chain, 1, 2, 3, 4, 5, 6, 7, 8, you can see here I have 2, 2, 7, whereas if I went the other way, if I started on this side, I would have 2, 7, 7, okay? And so the 2, 2, 7 is going to beat out a 2, 7, 7, and so we're going to look for 2, 2, 7 trimethyl octane, and so the answer is going to be C. Let's keep going. Question number 2. This one's an alcohol. We know the rule is when we're naming an alcohol, the longest carbon chain has to contain the alcohol or the hydroxyl group. And so we'd start numbering here because not only does the longest chain have to contain the hydroxyl group, but we want to give this hydroxyl group the lowest possible number. So we're going to go 1, 2, 3, 4, 5, 6, 7, like that. So we have a 5-methyl 2-heptanol. And so, yeah, the answer is going to be D, 5-methyl 2-heptanol. All right, let's move on. What is the IUPAC name for this compound? Again, another alcohol, so the same rule is going to apply. We're going to number the longest chain, 1, 2, 3, 4, 5, 6, but we want to give the hydroxyl group the lowest possible number, so we put it at the 3rd carbon here. So this is a 3-hexanol, and so we have the 2 methyl groups at carbon 5, and so we have a 5,5-dimethyl 3-hexanol. Here we go. Let's keep going. Question number 4. Which structure is 4-isopropyl 2,5-dimethyl heptane? Well, here the first thing I would do is I would look for the longest carbon chain. So I would look for that heptane, and you can see that we have one right here. 1, 2, 3, 4, 5, 6, 7. We have one here. 1, 2, 3, 4, 5, 6, 7. We have one here, 1, 2, 3, 4, 5, 6, 7. But the problem is here we have 1, 2, 3, 4, 5, 6, 7, 8. So we can scratch D off the list right away. But if we look at these, remember, we want to number this longest carbon chain in such a way that we give the first substituent the lowest possible number. And so when you do that, if you look at B, for example, we have 1, 2, 3, 4, 5, 6, 7, like this. And so we're going to put the isopropyl group first, right? Because I is prioritized over the M for the methyl groups, but this would be a 5-isopropyl, so that's not going to be correct. And if we look at B, there's no isopropyl group in it. Now, if we go back to A and we number it, going 1, 2, 3, 4, 5, 6, 7, we see that this is a heptane. We see we have methyl groups at carbons 2 and 5, so that's good. And then we have the isopropyl group at carbon number 4. And so the correct answer is going to be A. Keep in mind that when you're alphabetizing substituents like methyl, ethyl, propyl, isopropyl, etc., that normally prefixes like di, tri, tetra, we ignore those, okay? So we alphabetize according to the letter M here, but with iso, we don't ignore that prefix, so we alphabetize according to the letter I. So those exceptions would be iso. So iso and cyclo are the ones that we see the most. Those are prefixes that we don't ignore. And so you alphabetize any iso group according to the letter I, and any cyclo group according to the letter C. Another one is neo, but that doesn't come up a whole lot at this level of organic chemistry. Okay, question number 5. Which structure is 1,3,5 trimethyl cyclohexane? Well, I think this one is relatively straightforward. And if you look at C, we have 1, 2, 3, 4, 5, 6 in our cyclohexane. So we have a 1, 3, 5 trimethyl cyclohexane. So the answer is going to be C for that one. All right, let's take a look at question number 6. Something interesting about question number 6 is this is an alkene. Okay, we have an alkene here. But keep in mind when two of the substituents, so you see we have two methyl groups here, those are identical substituents and they're on the same carbon. This carbon I've labeled in red. So in that case, we don't have to invoke cis or trans or E or Z, and that's kind of, besides the point because it's not in any of the answers. Anyway, I thought I'd just mention that though. But much like the alcohol, we seek to number the longest carbon chain in such a way that we give the alkene the lowest, or the double bond, the lowest possible number. And so we name it after the first number, which is 2. So this is a 2-hexene, or you could call it a hex-2-ene. Either way is fine. And you see that we have methyl groups at carbons 2 and 5. So this is a 2,5-dimethyl hex-2-ene. And again, you could also call this compound 2,5-dimethyl 2-hexene as well. Either one is totally acceptable. Okay, let's move on to question number 7. What is the IUPAC name of this structure? We see here again our functional group is an alcohol, and so we seek to number the carbon chain in such a way that we give the alcohol the lowest priority, not the halogens. If you look at the order of precedence of functional groups, well, the only functional group in here is the alcohol, okay? So chlorine and bromine are not functional groups, and so we're going to number starting over here. 1, 2, 3, 4, 5, 6, okay? And so this is some kind of 2-hexanol or hexan-2-ol. And if you look at the answers, here they have a pentanol, and here they have a double bond. They have the 1-ene here, so it definitely can't be that one. Anyhow, so if we look at the other ones, we have in B, we have a 5-hexanol or a hexan-5-ol. And in A, we have a hexan-2-ol. So this has got to be the answer. So let's just check if the rest makes sense. And we have the 4-bromo, 5-chloro, hexan-2-ol. Or you could call this compound 4-bromo, 5-chloro, 2-hexanol. Either one would be completely fine. And keep in mind that the bromine comes before the chlorine because B comes before C in the alphabet, if you didn't know that already. Kidding. All right, let's take a look at... was I crossing off the wrong thing? Anyhow, I ignore that I even did that. All right, so now we're on to the actual question number 8, which is, and going back to the previous one, you can see that it's not a pentan one also. I kind of mixed that up there. Anyhow, question number 8, which structure is 4-bromohex-1-ene-3-ol? Okay, so we're looking for a compound that has an alkene in it and an alcohol. And you can see that they all have an alkene and an alcohol, but we're looking for the alkene to be on carbon number 1. And so if you look at A, we have 1, 2, 3, 4, 5, 6. On B, we have 1, 2, 3, 4, 5, 6. But there's no way the alkene could be on carbon number 1 in C or D, right? You see it's embedded inside. It's here it'd be on carbon number 2, and here would be on carbon number 3. So those can't be correct. So now let's just take a look at the rest. So if we look at A, we have 1, 2, 3 bromo. So we have the alcohol would be on carbon number 4, and the bromine is on number 3. So that's just completely wrong. But if we look at B, we have the alcohol on carbon number 3, so that looks good. And we also have the bromine on carbon number 4, so this would be 4-bromohex-1-ene-3-ol. So B is going to be the answer in that case. All right, question 8 down. Let's keep going. Now we're going to move on to a diol. Question number 9. You see this is a diol. It's got 2 hydroxyl groups in it. And so you can see this is a 7-membered ring. So this is some kind of cycloheptane 1,3 diol is the way you would name just the compound if let's say that methyl group wasn't there. And so this is going to be, like I said, a 1,3 cycloheptane diol, or you could call it a cycloheptane 1,3 diol. Either one is fine. And we're going to number it like this, 1, 2, 3, because we want to take the shortest distance between the 2 hydroxyl groups. We have the methyl group at carbon number 2. And so the answer to question 9, you can see, is going to be A. It's the 2-methyl cycloheptane 1,3 diol. All right, next one is another alcohol. Just killing it here with the alcohols. So this one, you see that the hydroxyl group is going to be on carbon number 1. And so we can do this by process of elimination. You can see that in A, the hydroxyl is on carbon number 3, so it can't be that. In B, the hydroxyl is on carbon number 2, so it can't be that. If we go to D, it's also on carbon number 3. So this one can be solved by process of elimination pretty quickly. You can see that with C, we have 1, 2, 3, 4, 5. That would be our longest carbon chain. So it's a 1-pentanol and, or a pentan 1-ol. And you can see that we have the isopropyl group at carbon number 2. We have the methyl group at carbon number 3, and so that one looks good. And so C is going to be the answer. All right, question number 11. What functional group does a peptide bond contain? Well, if you remember peptide bonds, those would have been mostly talked about in the chapter on amino acids and peptides and proteins and enzymes. And so also, if you studied biochemistry, you would know that a peptide bond is nothing more than an amide bond, but it's an amide bond between two amino acid residues. All right, question number 12, moving right along. Here we're looking at functional groups, and so we're looking for a few functional groups. We're looking for a ketone. So if we look at A, we can see we have a ketone here. In B, we got a ketone there. In C, we have a ketone here. And in D, there's no ketones, so we can cross that one off the list. Then we're looking for what? We're looking for an ester. All right, see if we can find an ester. So here we have an ester, here we have an ester, and here we have an ester. There's an ester in D as well, but there's no ketone in it, so we can cross that one off. And what else? Oh, I forgot the amide. So we're looking for an amide. There's no amide in A. There's one here in B. There's one here in C. And there's no amide in D either, all right? And what else? We're looking for an ether. Okay, trying to find an ether. Well, here we have an ether, and there's no ether in here. So the answer for practice question 12, if I can find my highlighter here, is going to be B. So make sure you know your functional groups. All right, here they're asking us which functional group is not in this molecule. We've got ether, amide, amine, and alcohol. And if you know your functional groups, this one's pretty quick. As you can see, we've got an alcohol here. You can see we've got an amide here. It's inside a ring, but that's still considered to be an amide. And then we also have an ether. We have a nice ether there, but there's no amine, okay? There is no amine in this compound, and so C is going to be the answer. Number 14, which functional groups are in this compound? And you can see from the answers that they consider an aromatic ring a functional group. So we have aromatic, okay? We have an aromatic ring. And so that's a possibility here. It's not in D, so we can cross that one off. What else? You can see that we have an amine. We have an amine here, so we have an amine, and we can cross B off the list. And the last one is we have an ester. So there's an ester here, and so the answer is going to be C is the answer there. And just remember that when you have an ester inside a ring, so if you have an ester in a ring, and it doesn't matter the size of the ring, I'll just draw another 6-membered ring. It is an ester, there's no doubt about that, but sometimes we refer to these as lactones as well. So a lactone is just an ester that's embedded in a ring like that. All right, question 15. A tertiary carbon atom is present in which compounds? All right, so we know that when we're looking at a tertiary carbon, it's going to have 3 bonds to carbon and then a bond to hydrogen. Sometimes we call these methynes when we're talking about a CH in proton NMR. Anyhow, you can see that we don't have any in 1, we don't have any in 2, in 3 we have one here and here, in 4 we have one here, and in 5 we have one here, so the answer is going to be 3, 4, and 5. All right, moving on to question number 16. Which forces are the strongest? You really need to know your intermolecular forces in organic chemistry, and here we have dipole, dispersion, hydrogen bonding, and cation, anion. Well, it's definitely not the dispersion force. And then we have hydrogen bonding and dipoles, which are other types of intermolecular forces. But keep in mind that A, B, and C, okay, these are all found in covalent compounds or between covalent compounds, whereas cation, anion, that's ionic. And we know that ionic forces are stronger than all the others that are listed here. All right, so if you want to write that down, we'll put in here ionic, okay? And the interaction between a cation and an anion is always going to be stronger than those other intermolecular forces between two covalent compounds. All right, which intermolecular forces are not present in the following compound? Well, keep in mind that if you want to have hydrogen bonding, you have to have a bond between hydrogen and oxygen, hydrogen and fluorine, or hydrogen and nitrogen. Sometimes we remember this as FON. Okay, you got to have one of those. And you can see that we have oxygens in this molecule, but there's no bond between oxygen and hydrogen. And so there's no hydrogen bonding, and so we can cancel out those two. Now, are there dipoles? Well, there has to be, because they're in both answers C and D, and you can see there's a dipole here, okay? There's other dipoles as well, right? Remember that this bond angle around this, or the molecular geometry of this oxygen here is bent, and so there's also going to be a dipole going in this direction here. And so we have dipole-dipole forces, and of course, all covalent compounds have dispersion forces, and so the answer is going to be D. The next one is 18. Which intermolecular forces cannot be exhibited by this compound? Well, this compound is called phenanthrene. You might have seen it in your organic chemistry class. It's got a formula that is C14H10. So if I just scribbled it down here, this is phenanthrene. I'll get my C14H10. Anyhow, and phenanthrene is a hydrocarbon, right? Any compound that contains only carbon and hydrogen is a hydrocarbon. And so the bond between carbon and carbon has a difference in electronegativity that is 0, right? 2.5 minus 2.5 gives you 0. But then if you compare the difference in electronegativity between carbon and hydrogen, which is the only other kind of bond in here, it's 2.5 for carbon, 2.1 for hydrogen. Well, the difference is 0.4, which is less than 0.5, which is considered to be a nonpolar bond. And so there's no dipole forces, there's no hydrogen bonding. And so which intermolecular forces cannot be exhibited by this compound? The only intermolecular force that can be exhibited by this compound are going to be dispersion forces. And so the answer is going to be hydrogen bonding and dipole-dipole. And in fact, you can remember that moving forward, that anytime you have a hydrocarbon, the only intermolecular force that can be experienced in between any kinds of hydrocarbons are going to be dispersion forces, nothing else. All right, what intermolecular forces can be exhibited by this compound? Well, here you see that we have an oxygen and a hydrogen together, and so we definitely have hydrogen bonding, so we can cross off both of these. And we know that if we have hydrogen bonding, we definitely have dipoles, and we have one here, and there's another one here. There's another one that could be drawn too. Anyhow, we clearly have dipoles here, and we know that all compounds have London dispersion forces if they're covalent compounds, and this is a covalent compound because it's only made out of carbon, hydrogen, and oxygen, so the answer is going to be D. Question number 20. What intermolecular forces can be exhibited by this compound? This is an ether, and again, you know the molecular geometry around the oxygen is bent, right? And so we have a dipole going, do a little better. We have a dipole going this way, and another one going this way. And so the net dipole is going to be in this direction. And so we have dipole-dipole, and we have dispersion forces as well, because all covalent compounds have dispersion forces. However, even though there's an oxygen in there, the oxygen is only bound to carbon. And so there's no hydrogen bonding in there, and so the answer is going to have to be A. 21, which compound has the highest boiling point? Well, if we take a look at A, it's not going to be that, because this compound only has ethers in it, whereas B, C, and D, they all have hydroxyls. Well, it's not going to be D, because D only has one, and it's got 1, 2, 3, 4, 5, 6 carbons. But C and B both have 5 carbons, but they have 2 hydroxyl groups, and so they're going to have higher boiling points than D because they're diols. And so if we take a look at these two, you can see that in C, I'd say a couple of things with C. Number one, that the hydroxyl groups are kind of embedded, or they're kind of inside the molecule, so to speak. But they could also hydrogen bond between each other, maybe, anyhow, we could draw something like that. Whereas in B, the hydroxyl groups are on the periphery, and so they're going to be able to interact with each other easier. And so I'd say that B is going to have a higher boiling point. Next question, number 22. It says which compound has the lowest boiling point. So we're looking for the one that boils the easiest. These are all cyclic compounds with a hydroxyl. So the first one is cyclohexanol. Then we have cyclopentanol, cyclobutanol, cyclopropanol. And cyclopropanol is going to have the lowest boiling point because even though they all have the hydroxyl group, well, after that, it would be based off of molar mass. And since cyclopropanol is the smallest, it has the lowest molar mass, and so it's going to boil the easiest. It's going to be easier to break those intermolecular forces to convert the compound from a liquid to a gas. All right, question number 23 says, rank these compounds from lowest to highest boiling point. Well, the highest one is going to be the diol. This one here, the diol, so 2 should be the highest one. And then the lowest, or the one in the middle, is going to be number 1. And so let's see this one here, so we can cross this one off here. And then the last one, number 3, is the ether, and it only has dipole-dipole forces, doesn't have any hydrogen bonding. So again, the rationale is 3 is the lowest. It only has dipole-dipole and dispersion forces. 1 is somewhere in the middle because it does have hydrogen bonding, but not as much as 2. And then 2, and it also has dipole-dipole forces, of course, and London forces. But 2 is going to be the highest because it is a diol. So the answer is going to be D. Question number 24. Rank these compounds from lowest to highest boiling point. Well, the highest one is going to be the one that has the hydrogen bonding, which is going to be the butyric acid. So that's a carboxylic acid. The next one, if you look at 1 and 2, in number 1 you have dipole-dipole forces here. And 2, you have dipole-dipole forces here, right? They both have an ether, but in number 2, you also have the dipole-dipole for this ketone here. And so going from lowest to highest, it should be 1, 2, 3. And so the answer for 24 should be A. All right, next question, question 25. I think all of these compounds are isomers of each other, right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yeah, I think these compounds are all C6H14, and so they're all isomers of each other. They're all hydrocarbons. They only experience London forces or London dispersion forces, nothing else. No dipoles, no hydrogen bonding, and so which one's going to have the highest boiling point? Well, that's going to be based off of branching, and you can see the only one that has no branching is A. And so the less branching you have, the higher the boiling point is going to be. And I don't want to take up too much time in the video explaining that. But the rationale is because, you know, if you had a second molecule of this, right, you can see how, right, they're going to be able to pack efficiently, and we can have lots of intermolecular forces in between the two, lots of dispersion forces. So the answer is going to be A, the one that is less branched is going to have the highest boiling point. The one that is the most branched would have the lowest boiling point. All right, nonane has the greatest solubility in which solvent? And so nonane is just a 9-carbon hydrocarbon, C9H20, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is a nonpolar compound. It only experiences London forces, and you remember the axiom, like dissolves like. That means that nonpolar compounds are going to dissolve in nonpolar compounds. Well, ethanol has a hydroxyl group, and so it's a polar compound, right? It has hydrogen bonding, as does water. Water is also polar. And then if you compare tetrachloromethane and dichloromethane, and I don't have a lot of room here, but if I just draw tetrachloromethane, which would be tetrahedral, right, is completely nonpolar because any dipoles in here are going to completely cancel out. And so tetrachloromethane is like nonane in that it is a completely nonpolar solvent, whereas dichloromethane, which we only have 2 chlorines, and then we have 2 hydrogens like this is going to have a dipole in it, right? It's not spherically symmetrical, so it does have a slight dipole. And so again, if we obey the axiom, like dissolves like, nonane is nonpolar and tetrachloromethane is completely nonpolar. I'll redraw it here. Okay, so tetrachloromethane is completely nonpolar. All right, deprotonation of a carboxylic acid in question 27 increases its solubility due to the formation of. Well, this question actually shows up a couple of times kind of in this ACS study guide. And what happens when we take a carboxylic acid, okay, if we take a carboxyl group like this, if I can just zoom in a little bit, and it says here deprotonation. So when we deprotonate this, well, if we remove the proton with a base, then we end up with a salt, right? We end up with an ionic compound. And so we have an ion, and that's going to interact with the dipole in water. Now, I don't want to take up too much time showing you that, okay? But the negative charge on the oxygen that I have here is going to interact with the delta plus, you know, in the water molecule like this. We have our delta plus here. And so there's going to be an interaction here, and we call that an ion dipole interaction. And so for 27, the answer is going to be C. So make sure you also know ion dipole interactions and ion-induced dipole interactions and those kind of things, right? In organic chemistry, you're expected to go a little bit beyond just the dipole, hydrogen bonding and dispersion forces, and know some of these other intermolecular forces as well. All right, rank these compounds from least to most soluble in hexane. Well, hexane is a hydrocarbon, right? It's just a straight 1, 2, 3, 4, 5, 6, 7 carbon hydrocarbon. Its formula is C7H16. It's completely nonpolar. And so if we look at these compounds, well, ethanol is a polar compound. So if we obey the axiom like dissolves like, ethanol is not going to be very soluble in hexane. Then we have cyclopentane, and cyclopentane is a hydrocarbon, and so it is completely nonpolar, okay? And then dimethyl ether is also polar, okay? But dimethyl ether doesn't have hydrogen bonding, right? Ethanol has hydrogen bonding, okay? And I'm not going to draw the structures right now, but dimethyl ether is an isomer of ethanol. They both have the same molecular formula, C2H6O, but dimethyl ether only has dipole, and London forces. And so if we obey like dissolves like, dimethyl ether is going to be more soluble in a nonpolar solvent like hexane than ethanol will be. So it should be the least is 1, then 3, then 2, and so the answer is going to be D, like that. Question 29, I looked at the the answers to these, not the solutions. And this one, I'm not 100% sure on this one because they're saying that the answer is B in the ACS study guide. But if we're talking about diethyl ether, so diethyl ether would be this compound. Let me just get my black pen here. Okay, so diethyl ether would be this. Okay, and if we obey the axiom like dissolves like, okay, diethyl ether's strongest intermolecular force is going to be a dipole, and it also has London forces. Now, they're saying that, number 1, the cyclohexane carboxylic acid is going to solubilize the best in diethyl ether, but I would argue that it might be 2 because this is called 1,4-dioxane, this compound, 1,4-dioxane, and you can see it's got 2 ethers in it. So it seems to me that 2 would be the most soluble, but again, the solutions manual is saying that it's B, but I would go with, you know, based off of that, I would go with C or D. So anyhow, I would rank number 2 as the first one, but again, the solutions manual is saying number 1. But going beyond that, the one that's going to be the least soluble, and it would be 3. And so I would say 3, 1, 2. I would say the answer is C, but they're saying 3, 2, 1. Okay, so we'll just go with the ACS study guide. I'm not sure. And maybe you could ask somebody about that, somebody who knows more about organic chemistry than me. But I would say that one is maybe debatable. Anyhow, all right, let's take a look at number 30. And 30 is kind of a rehash of question 27 in a way. It says here, addition of which of these will increase the solubility of this compound in water. Well, this compound is a carboxylic acid. You can see it's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this would be decanoic acid or 1-decanoic acid. Anyhow, what's going to increase the solubility of this compound? Well, you guys know, you all passed Gen Chem 2, that when you take this and you treat it with sodium hydroxide, right, you're going to end up with a carboxylate salt. All right, you need to know acid-base chemistry. And when we make a carboxylate salt, sure, is a carboxyl group soluble in water? Yes, because of hydrogen bonding, but a salt is even more soluble in water. And so the answer is going to be sodium hydroxide. We make that carboxylate salt, which is more soluble in water than just the neutral carboxylic acid. And there you have it. Chapter 2. What is it? Structure, nomenclature, and functional groups.